So let's say E, G, okay, then K. These are the unit vectors in the direction of E is in the direction of X, G in the direction of Y, then K in the direction of Z. So if you count the vector product E vectorial G, it will give you a vector such that, then I said these are orthogonal. Orthogonal, this word means perpendicular to each other. So one interesting property about vector product is the vector product of E vectorial G is equal to um, a vector, and that vector is such that, don't forget to put an arrow. Usually with the people that I'm teaching, I've noticed that they forget to put an arrow when they are dealing with vectors. Once you forget, a vector is defined to be a physical quantity that has got magnitude and direction. So if you don't show me the direction, then that you're not giving me a vector, you're giving me a scale. Then this one is a vector product. And in other books you find a cross. You're carrying out the vector product. As the name implies, you get a vector. Okay. Then another interesting property about vector product is if because a vector product is also defined, for example, u vector a v is also defined to be, you get the magnitude of u, and this is an notation for magnitude for a project that are just joining us. You also get the magnitude of v, then you find the sign of the angle between u and v. Okay, so I'm just going to remind you a bit. The sine of zero is equal to 0. Okay, so this finding, this is a definition of a vector product. So if those two vectors that you have, if the angle between them is 0, it means that here the angle between them will be 0. So it means that sine of 0 will be 0. Therefore, it will give us 0. If, notice how I'm putting an arrow on the 0, because it always gives us a vector. Even if that vector is 0, you indicate, you put the arrow. Don't forget these things. So if u and v are in the same direction, that is, the angle between them is 0. So let's say this is u and maybe this is v. So they're in the same direction, the angle between them is 0. So this means that the vector product of the same vector is 0. Why? Because the same vector and the same vector, the angle between the same vector is 0. Okay? So from the properties of sine, you can tell when you're given the vector product. Let's say if I've got E vectorial E, you know that E and E are the same vector, so this is 0. Okay, then you don't forget the direction. Okay, so those are interesting things about the vector product. Then I'm also going to show you why, through calculations, I'm going to show you why the vector product of E vectorial G is equal to K. Okay, are you following? Reactions, if you're following. Reactions. Okay, thank you. Other people, others, then yeah. Boniface, Caleb, yes, Cholo.
I don't know, but I think you're moving a bit too fast.
I'm a bit too fast. Okay, yeah, sorry, because normally I'm not supposed to, like, it's like I'm out of topic. I'm out of the things that we're supposed to look at. I've only learned that you haven't looked at anything in Mechanique du Poids, so I'm forced to, like, you get, so don't worry. Okay, I might be a bit fast, but this when I start looking at the things that you need, I'll be using vector product. So I'll tell you, okay, I'll be slow when I need to. So don't worry.
All right.
Okay. All right. Yeah. Caleb. I don't know if it's Caleb or Caleb. Are you there? Caleb, are you there? He's been giving me negative reactions. Caleb, are you comfortable with talking? Okay. Okay, continue.
What?
Yes, Caleb, are you following? Ukonka, ule konka?
Yes, you are just moving a bit too fast.
I'm moving a bit too fast. Yeah, okay. So basically, my program for today has been disturbed because of certain things that you didn't learn. So that's why the things that you're learning, you learn them in Mécanique du poids. That's a topic in Mécanique du poids, a vector product. Yeah, okay, but okay, let me just be slow. Uh, if I tell that we extend maybe 20 minutes, obviously we won't want that, you get. So
It's okay.
it's okay. Yeah, so yeah, okay. Yeah, and when I'm fast on certain things, it's because I know that you won't be examined on those things in my course. So I want to teach you like the actual things. Then some things I'll just tell you, okay, memorize them as they are because for now you don't understand. You haven't learned a thing on coordinate system apart from the people that are in my special classes. Then so I'll just tell you to like whenever they ask you to find, for example, the gradient, this is a formula. Memorize it for now here. Okay? Yeah. So for example, we defined E and G in our first session. Okay? So E is a unit vector. So E can be written as a matrix, can be written to be 1, 0, 0. I said this is in the direction of E, direction of G, direction of K. Okay, then G can also be written as what? 0, 1, 0. Okay, then the vector product of E vectorial G will be calculated to be, then I'm also recording, so yeah, 1, 0, 0 vectorial 0, 1, 0. Okay, so what is K? What is a vector K? K is also defined to be 0, 0, 1. That is washimya wasakasha muri z-axis because k is a unit vector in the z direction and it is of a magnitude of 1. So if you're writing as a matrix, you just put the magnitudes. Okay, if you're writing a vector as a matrix, you put the magnitude. So it's a magnitude of 1 in the direction of z, which z direction is represented by k. Okay, so now since from the vector product rule, we said that if such that if I count the vector product of two vectors, this is a vector g and this is a vector in the direction of x, it will give us, then these are perpendicular to each other, it will give us a vector such that that vector is perpendicular to both of them. So in short, it has to give us k, right? So we're trying to demonstrate that it will give us k. That is, if I count the vector product of these, supposed to give us this k, this vector 0, 0, 1, which is equal to k. Okay, so just a demonstration on the vector product so that you fully understand how you carry out the vector product. For this, or everything that I'm teaching you now is mécanique du poids. So 1, 0, 0. This is how you write E vectorial. Then G, you write it as 0, 1, 0. Then, so we'll carry out the vector product. What we'll do, we'll cancel the first part, then we'll write the remaining as a matrix. Normally, I don't, for me, who is experienced, I don't even write it as a matrix, but for to demonstrate to you guys. So you say 0, 0, 0, 0, 1, 0, 1, 0. Then you carry out the vector product, the determinant of this matrix. Let's say this matrix is A. You find the determinant of determinant of determinant of A. Okay. So how do you find the determinant of A? Major minus minor. Then here when you're finding, you know that the vector product should give us another vector. So that vector will have three components. The first component, the second component, and the third component. Right? So how are you going to find the first component? You cancel out the first element. Then you carry out the determinant of the remaining elements. So the determinant used to find determinant. So 0 minus 0, 0 multiplied by 0, then you subtract from, then here So here you put plus, negative, plus, so that you remember. So 0, 0, 0, 0 multiplied by 0, it's 0. Then, so 0 just for to show you what I'm doing. Then 0 multiplied by 1. Okay. Then the second part you put negative because there's a negative here. Okay. Then negative. Then what you do? You cancel out the second part. Okay. You cancel out the second part. Then what do you remain with? You remain with your new matrix A will be. You remain with 1, 0, 0, 0. Okay. Then you do the same. You find the determinant. You find the determinant. You find the determinant of A. How do you find the determinant of A? Major minus minor. Okay, so that is going to be 1 multiplied by 0 minus 0 multiplied by 0. Then the third one, you do the same. You cancel out the last element. Once you cancel out the last element, you have a new matrix. What matrix are you going to have? You're going to have 1, 0, 0, 0. 1, 0, 0, 0. Then you count it. Okay. Oh, when you cancel out the last part, right? Yeah, cancel out the last part. So we're going to have 1, 0, 1, 0, then 0, 1. Yeah, 0, 1. Yeah. Okay, I'd have been shocked. So you got the vector product, the determinant. How do you find the determinant? But here there's a plus, so when you add the plus, it doesn't change anything really. So you just say 1 multiplied by 1 minus 0 multiplied by 0. Okay, so here when you do calculations, what are you going to have? You're going to have the first part to be 0, the second part to be 0, the last part to be 1. Then by definition, what is this? This is none other than car. Okay, so I've just shown you that the vector product of E vector A G will give me car. And what is an interesting thing about car? Car is perpendicular to both E and G. So what is a vector between E and G? So this is E is defined for people who are just joining us as a unit vector in the direction of x. Then G is defined as a unit vector in the direction of y. So the angle between them on the Cartesian is 90. So by the also we can also apply the definition if you want to find 0, 0, 1. We can also apply the definition. What's the definition of vector product? I said that the definition of vector product E vector A G is defined to be the module of E, the magnitude of E, or they say in French module of E, multiplied by the module of G, module de G, multiplied by the sine of the angle between them. Then what is the angle between E and G? It's just 90. Or pi, here I'll be using pi over 2, be using radians. Pi over 2 is 90 for people. Pi is equivalent to 180, so pi over 2 is 90. So what is the magnitude of E? This is a unit vector. So 1 multiplied by magnitude of another unit vector 1. Then what is the angle between them? Multiplied by what is the angle between them? The angle between sine 90 is what? Is 1. So it's going to give us 1. Okay. Then in the direction of car, you put the direction E vector G will give us the direction car. Okay. So yeah, when you're finding the module, this is a definition. So you look at the angle between the two vectors. Then you say sine is sine if it's not 0, if it's not 0, sine of 0 is 0. So homework. I want you to find E vector A E. I also want you to find G vector E. Okay, very simple. Using using their definition, that is E is equal to is written as 1, 0, 0. Then so I'm going to delete this. Then you count the vector product, so just for you to practice on the vector product. So I don't know how you're going to take a screenshot of this. This will be your first homework with me. Yes, Muida.
Yeah, I have a question. on the part where you're putting the sign with an angle, like where are you getting that angle from? I'm a bit behind.
Okay, thank you for your question. Uh, I'm sure I've deleted. No, here, here.
Yes.
Okay, so when you're carrying out the vector product, the definition, when I say this is the module of this vector, is defined by the module of E, that is the magnitude of E, multiplied by the magnitude of G, then sine of the angle between them. What is the angle between E and G? E and G are none other than, if you have got your Cartesian coordinate system, that is X and Y. At the beginning of the session, I said that we would define a unit vector E, that is a vector with a unit of 1. So this unit vector E, and we also define a unit vector G in the respective direction of Y and X. Okay, so the angle between E and G therefore is 90. So sine, but here we're not going to be using 90, we're going to be using pi over 2 because pi represents 180. So 180 divided by 2 is 90. So we're going to be using radians for people who did radians. But for now, just know 90 is pi over 2. So that's how I found the angle between E and G is 90. So sine of 90, which is 1. Have I answered your question?
Yes, you have.
All right, thank you. Chodwe, you're my spokesperson or whatever. You can just speak. You've got the right to speak anything.
All
Yeah.
right. My question is, how are you? You said earlier that there's also a scenario where you get sine 0.
Yeah.
So it's different from this case here.
Sine 0 is 0. Sine 0 is 0. So you get sine 0. You ask yourself, what is the angle between the vectors, between the vectors that I'm working with? Normally, let me not confuse you. Normally, this is the definition, this formula that I wrote here. When I say magnitude of the vector product of two vectors is defined, this is the definition of the magnitude, E multiplied by G. Okay? Then sine of the angle between them. We put this. Let's say if I had E vectorial G. So this will have vectorial E itself. So I'm going to apply the definition E sine of E. So what's the angle between E and E? The same vector. That's 0. This is the case where I'm going to have 0. Have I answered your question, Chodo? When
Or yes.
you just ask yourself, what is the angle between E and E? This is the same vector, really. There's no angle between them. Okay, you're not going to be using this formula. You're going to be applying what I've just told you. You're going to be applying whereby you have 1, 0, 0, vectorial 1, 0, 0. This formula is just there because if you see E vectorial G, you for the Moroccans they know directement they will know that okay, this is 0, this is going to give me 0. E vectorial E will give me 0. Why? Because obviously from this definition I'll have sine of the angle between them. So sine of 0 is 0. Directement they will know that everything will be 0. But if you want, you can apply what you're going to be using most of the times. If anything, I don't remember a time when I ever used this. This is just there to show us that if the angle between two angles is 0, it's 0. Just to show us why that property is true. Okay, my battery. But most of the times you're going to be applying what I'm just from teaching you, where you cancel out the first part, you do what, and from the homework that I've given you, I want you to do this. Forget about the angle between them. So there are two ways of finding the vector product, but this main one is the one that I want you to get Good. I'm just showing you why the vector product of two vectors that are of the same direction is 0. Have I answered your question, Chodo?
Oh yes, it's answered.
All right, Zikomo. Any other question? Okay, now I can start teaching my things because I'm feeling sad. Okay, now there's some mathematics that you're going to learn that I'm supposed to teach you. So I've missed on a lot of things. Okay, so we define a vector OM to be x, ex plus y, ey plus z, ez. For people just joined us, I emphasized on why whenever you're writing a vector, s'il vous plaît, this is a mistake that I've noticed from the students that I'm teaching in my special classes. Don't forget to indicate the unit vector in those respective components. Okay? Then they will just ask you a question. Give us the vector OM, but they'll never ask you that. This is the simplest one. Give us a vector OM in the Cartesian coordinate system. That's the only question that they'll ask you. So they expect you to know that the Cartesian coordinate system has got x, y, and z. I've made videos on the coordinate systems. For those people who are interested, you can look them up. I will send you the video at the end of this session. I will send you the link to the video on my YouTube so you can watch them. I've tried to explain to my best. So this is how you write OM, or alternatively you can write OM as, if you're too lazy to indicate the directions, you just say X, Y, Z. This is also marked unless specified. Okay, so this is how you find OM. So we're not going to find this. This is now mécanique du poids. This is just the introduction. So you'll be dealing a lot with vectors. So you find the Vx is just representing the component in the x direction, the component in the y direction. So this is how we basically, yeah. So now my things. So now one mathematical tool that we're going to learn today is the gradient of a function. So if you have a function, and then you are asked to find the gradient of that function. So notice that the gradient has got an arrow. So which means that this gradient is a mathematical tool that converts a function, a scalar. Notice that whatever is in here represented by f is not usually always a scalar. When I say a scalar, I mean something that just has magnitude d but no direction. So it converts a scalar into a vector. This is none other than a vector. Okay, this is a vector. Why? Because it has got directions. It has got unit vectors showing us direction. S'il vous plaît, when you are finding the gradient is a mathematical tool that converts a scalar f into what? Into a vector. This is why the gradient has got an arrow on top. Then we have another mathematical tool called the divergence. Divergence is a mathematical tool that converts a vector. As you can see, this is a vector v with an arrow. It converts this vector into a scalar. As you can see, the overall everything doesn't have an arrow. So it converts, this does the opposite of gradient. The divergence does the opposite of gradient. Okay, so you are going to find a lot of gradient, divergence, rotationnel. Now, it's also my job to give you the physical, la signification physique de cet opérateur. Quel opérateur gradient? La gradient is a very important operation. So I'm going to explain to you what it implies in physics and why we use it in physics, the importance of this mathematics. So Gradient is usually difficult for people to visualize, so I'm going to start with the divergence. This is how I understand. If you just follow nicely, you understand what I'm going to explain to you now. You're going to find physics very, 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 very simple. People fail to connect, even people who've passed it fail to connect the mathematics to the physics. Therefore, by some they find it difficult. By some they end up swata. Okay, so I'll try to explain to my best. So I'm going to start with divergence. So how do you find the divergence or what's someone chan? So divergence, diverging comes from the word diverging. Divergence, I don't know if I've spelled it right. It's represented as div of a vector. What you do is you find the partial derivative. I'm also going to explain to you what partial derivatives are for people who don't know. The partial derivative of the x component of that vector. Notice there's no direction on the vector because it converts a vector to a scalar, plus the partial derivative with respect to y, okay, plus the partial derivative with respect to z. This is how you find the divergence in the x in the Cartesian coordinate system. When you say Cartesian coordinate system, anything that has to do with x, y, and z, this is what so you find that vector v, you decompose it. Obviously, that vector v will be written as what? Vx in the direction of x plus vy in the direction of y plus vz in the direction of z. Okay, then the division, so this was initially a vector. If I pass on this mathematical operation, I'm going to have a scalar. This is a scalar. Why is this a scalar? There's no direction. You don't see anything that has to do with direction here. There's no arrow here, in short, in simple terms. So now divisions, what does it mean? I'll give an example of what you'll be working with. For example, you'll be working with the show electrostatic, this vector E. For now, just take it as a vector. I'm going to define it. So this vector E is an electric field vector. So I'm sure this word is now familiar to you people, the electric field. So whenever you have a charge, which is what we're supposed to learn today, whenever you have a charge, a positive charge, so whenever you have a charge and another charge, a negative charge, you know what positive and negative will do what? There'll be an attraction. But when this charge was alone, it created an electric field around it. And this is how we represent an electric field around a positive charge. We represent that electric field as vectors that are diverging away from this point charge. This is how, such that if this negative charge comes into its vicinity, there will be that force of attraction. There will be an attraction. Okay, there will be that force of attraction. Okay, now this this electric field or show electrostatic, in French we say show electrostatic. You will learn about show electrostatic hopefully next session, so please join. So it's represented by this vector. Then for a negatively charged, we represent the show electrostatic, we represent it as arrows diverging or converging, but I'll use diverging into a charge. I'm going to use the same word diverging from the divisions. So divisions of a vector, for example, the divisions of this electric field it's just you quantifying, how much this vector is diverging. Okay, in English this is the divisions. So this is what you will not even be taught by the professors that are going to be teaching you. So I'm giving you, because when I'm studying I like get into details of whatever I'm given. I try not to swat. So this knowledge is specifically how I understand these things after digging very deep, because Kuskuru bakazamba mpasana ncha, but find the divisions of E. For example, the divisions of the magnetic field. When you start looking at the magnetic field later on, you find that it's 0. They will never explain to, oh, this is this is a scale. They'll never explain to you why the divisions of B is 0. They'll just give you the divisions of B is 0. So now, for you to understand why the divisions of B, so B is usually represented, B is usually circular like this. This is a magnetic field. We'll get into it later on, don't worry. But for now, just take this vector B is represented. It's always circular. So there are no vectors diverging for B. Therefore, mathematically, the divisions of B is what? 0. Why is it 0? Because B by nature, or the magnetic field, which is represented by B, by nature does not diverge. It's circular. There's also another mathematical notation that we're going to learn, rotation. So these three, gradient, divisions, rotationnel, are mathematical tools that are used to quantify some physics concepts. So for a vector that is diverging or converging, which we just say diverging inside, they have to have, for example, the divergence of E has to have some value. Why? Because by nature, an electric field is always either diverging or converging or diverging inwards, depending on the nature of the charge, that is, whether it's positive or negative. This is super information that you maybe, had it not been for learning with me and not doing a research, you might even never know them and end up getting a 10 in electricity or physics 1 because of that, or having trouble like trying to, because they'll give you a lot of formulas. So this is the starting point. Then the rotation just shows how circular or the curling of a vector. So the rotation of B is what? Is a certain value, is not 0. Why? B by nature rotates. So if you want to know what it will give, you have to know what B and E is. For example, what is the rotational of B, of E? Rotation of E is what? Rotation of E is 0. Why? E doesn't rotate, it just diverges. Okay? So this is how I remember these things. They will just give you rotation of E is 0. The rotation of B, they'll give you some value. The variance of B, but paired is 0. So like it's like you start mixing, we start seeing rotation of E, rotation of B, you start like mixing them because you didn't understand in the first place. So am I communicating, s'il vous plaît? These are the basis of our module. This is the basis of our module. Am I communicating? I'll need your reactions. Am I communicating? I've already received few reactions. Am I communicating? I've received a negative reaction. The person who has given me a negative reaction, you are at liberty to tell me what's going on. The person who gave me a negative reaction, s'il vous plaît, are you in a space to talk? I haven't received reactions from other people.
Hello, can you hear me?
Yeah, I can hear you, Mwamba.
Yeah, I kind of lost the connection here, and whatever you said about the divergence,
Yeah,
I did
divisions.
not get. Yeah, the
Divisions.
divisions, I did not get it at all. I'm
Okay.
really sorry for that.
No, it's okay. It's okay. It's not. It's a network. Don't worry. Even if I said I explained something and someone they don't understand, you are at liberty. Okay, this is a space to
Yeah,
learn. No one is more intelligent than the other. So if someone didn't understand, you are at liberty to take me back. What I want is giving people information that will last, because I know when you start your school, you start over again. So I want to give you. I'm not really going to manage to teach you the entire course, but I'll make sure that you're able to study the course on your own. When you see certain terms and notations, you're not afraid of the course. So people will follow nicely with me, and people are very who wants to learn. usually these are things that are very easy to understand, but the way they explain physics, they don't really explain physics the way it's supposed to be explained. That is the intersection between mathematics and the physics. So these three mathematical tools, they are just mathematical tools that are used to quantify these physics concepts: rotation, rotationnel, divergence, and gradient. So I've explained to you using examples of the same the same uh, notations that you're going to find. Okay, so divisions is just easy as the name implies. So a vector has to be if a vector is not diverging, just know that so for example v is rotating. It's a rotating vector. So divisions of v will be 0, but may the rotation of v will be a certain value, will be a certain value. That's how you remember. So now divisions is quantified in mathematics. How do you calculate how much the vector is diverging? Very simple. So I'm going to introduce you to a new operation. This operation will be helpful to remember for you to remember the formulas, because so when you calculate divisions, in your head you should know what you're calculating. You're calculating how much there's certain vector is diverging. Even if you're not seeing it, they'll give you components of that vector. Just know that you're calculating how much that vector is diverging. The rotational vector, how much that vector is doing what? Circulating. Okay, this information is very important. So, so I'm going to introduce you to a new operation called the Nabla. Nabla. Nabla Nabla operator. This Nabla operator helps us remember the formulas for divisions. They also help us remember rotation. They also help us remember gradient. Then I haven't explained gradient. Gradient is just none other than so for gradient, it's very difficult to visualize, but gradient, take it as the, because you know what gradient is, the steepness or the slopeness, the steepness of a slope. Okay, how steep? For example, if you've got a straight line, the gradient is 0. So for you to have gradient, you have to have something, a vector that is bent in some way to, for us to have it just measures how steep that slope is. Okay, that's what gradient is. Basically, gradient and differentiation. Gradient is a base of differentiation. So with gradient, it's like you want to know how steep that slope. For example, you want to know how steep that slope is with direction, because it's a vector. So gradient will take a function. Then once it takes that function, finds how the steepness of that slope, then it will also show you the direction that it is taking. So for example, you find gradient to be like this, gradient to be like this, gradient to be like this. Therefore, the rotation of gradient of whatever, let's say gradient of what f, the rotation of gradient is 0. But you put an arrow because rotation gives us, I didn't say much about rotation. Rotation gives us a vector. Divergence gives us a scalar. Gradient gives us a vector. So the rotation of any gradient, because the gradient just gives us a gradient is not a rotating, the gradient is not a rotating vector. So you find this property. Actually, let me even show you that I'm not speaking from without. Let me show you how your professors will represent them to you, and yeah, what you're going to see. You're going to be using this a lot. Let me show you. Here it's even written théorème très utile pour les applications. One of the most important is the rotation of a gradient. What is the rotation of a gradient? Is 0. So you can only remember this formula because you're going to be using this formula a lot. You can only remember this formula if you understand. Okay, so the rotation of a gradient is 0. So gradient, you take it as a slope. This vector is not rotating. So the rotation of this vector inside has to be rotating somehow for us to have a value. Then rotation gives us a vector. So a 0 you put a what? A r. So you've seen. So the rotation of a, okay, the rotation of a vector, let's say rotation of a vector. If a vector is rotating, it means that it's rotating, right? So if you find the rotation of a vector gives us a value, then you find the divergence. The divergence of rotation is also 0. Why? Because if this vector is rotating, it means that it's not diverging. So we can't find the divergence. If a vector is rotating, it's not diverging. For it to be diverging, it should go towards a certain point. A very good example of a point is a point where a system where we have the divergence is non-zero is when we have so you've seen my rotation. So these formulas you only understand them bit by bit if you understand what rotation divergence is. So a good example is an electric field. Then I defined an electric field to be, for example, if you have a charge positive, how many minutes is that? Is that a hand or minutes? Negative. Then I said that, so here's what is going to happen. The electric fields will come out, always diverge away from the positive and diverge into the negative, like this. This is how you represent the notation. So I've got a positive charge and negative charge, and therefore um, there will be an attraction. So here is an electric field. So going this, if going this direction, they'll go this direction. So here is an electric field. So um, at this point, okay, the electric field is written. This is how we represent the electric field. Then at this point, this is how we represent no, going inwards. This is how we represent the electric field going inwards. Then when they come into contact, they'll from the positive, this is how from the positive to the negative. So this is electric field and this is the electric field. Okay. So uh so you also have to know how we represent the electric field. Then the electric field is diverging from a certain point or diverging into a certain point. Therefore, its divergence of electric field is non-zero. Mais rotationnel of E is 0. Then rotation gives us a vector, so 0 will have an arrow on top. Am I communicating? Very simple concept that you can understand. Nothing is difficult, it's just new to you. One way of learning, don't have a mindset of giving up. Have that curiosity to learn. If you have that curiosity to learn, you're going to go further with your education. I'm not going to say further with your life, because the way life is, you might job by a lot but not go anywhere. So you might go further with your academic education. Yeah, so now going after explaining the physics meaning of divergence, gradient, and the rotationnel, I'm now going to explain the mathematics part. So you're now trying to quantify gradient. This is the formula that you apply. The partial derivative of f with respect to x in the x direction, the partial derivative of f with respect to y in the y direction, and plus the partial derivative of f with z. This is how you find the gradient in the Cartesian coordinate system, because the unit vectors that you have, they are the best vectors of the Cartesian coordinate system. So you can also find gradient in other coordinate systems. I'm going to give you that. So I'm going to show you how we find gradient, divergence, and rotation mathematically. I've explained to you what it means physically, if there such a word exists. So yeah, then we're going to try to work around these new terms, these new mathematical tools that we've learned today. So I'm going to start uh, with gradient. So if you want to remember gradient, you introduce an operation called Nabla. Okay, so what is the definition of Nabla? Nabla is defined as the partial derivative of x in the e direction plus the partial derivative of y in the z y direction, and plus the partial derivative of z in the z direction. So notice that when I write car, I'm saying z direction to remind you that car is just a unit vector in the z direction. So car g e. Then of course, you can represent Nabla. Nabla is a vector. It's just an operation. Doesn't mean anything. It's just an operation to help us with remembering some formulas. These three important formulas. We're trying to quantify rotation, divergence, and gradient. So I'm going to say the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. This is how you write, and you just get the magnitudes. You forget about the vectors whenever you're putting them in a matrix. The same basic rule of vectors. Okay, apa sinairembe mwisho. Um, so you do like this. Okay, okay, like this. Otherwise, yeah. So this is how you present it when you're doing. Because I said when you're doing calculations, I advise you use matrices instead of using these notations. It will be helping you. Then convert it into a vector, this vector notation later on. So this is how you represent Nabla. Partial derivative, we call this del over del x, del over del y, del over del z. So I'll show you why this Nabla operation is important. For example, for example, if you Chodwe, do I have a notification for how many minutes I'm remaining with?
Yes, you're remaining with 9 minutes.
9 minutes. Oh my god. So, for example, gradient. So once you know the Nabla operation has to be memorized. It's just an operation, has to be memorized at all cost. So the gradient of f will be defined as Nabla f. Nabla is a matrix. So when you multiply a matrix by a scalar outside, what does it mean? It means that so you write, so you have to remember gradient is equals to Nabla of f. Okay, so what is Nabla? You define Nabla according to the definition. This is Nabla. This is why I'm going fast. The way time is moving. Or maybe it's not just moving. Then you multiply by f. This is what it means. Then according to matrices, how do we operate on matrices? If you have got a number outside, what do? You just multiply everything by what is outside. So this is how you find the gradient. So you multiply f everywhere. This is how you find the gradient, of f. So all you need to remember is the operation Nabla written as a matrix, and then you also have to know the gradient of f. I'm just multiplying that Nabla multiplied by f. So such that then I apply the matrix operation where I multiply f everywhere. So then if I write this, I can now convert this into a what? I can convert this into a vector. So this means that del f over del x in the direction of e plus del f over del y in the direction of g, then plus del f over del z in the direction of k. People tend to forget these directions. If you play, don't forget these directions. I'm going to give you an exercise. Don't forget these directions. Okay? This is basically how you remember the formula. So you have to know this number operation because you're going to be using the number operation everywhere. With the rotation divisions, you're going to be using this number operation. So for now, let us look at an example on how to find the gradient because of the minutes that are remaining. So let us now look at an example. So for example, if you have been given a scalar function, a function let's say x squared plus y squared, the simplest function plus zy squared. So now, with this example, pay attention. You're also going to learn a new thing, which is partial derivative. For some people who are just seeing partial derivative for the first time, I'm sure most of you are, if not everyone. So the first thing that they tell you, find the gradient of f. So with gradient, you are converting f, which was a scalar. You can't see any direction here, of course. So you're converting it into a vector. So what do you need to remember? You need to remember that this is the nabla of f. Then, meaning you'll be forced to remember what nabla is. Nabla is what? You just do this. Partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Very simple. Then, gradient means I'll get this, okay, I'll get that multiplied by f, which means if I'm multiplying a scalar outside, I just multiply it to every component like this. So gradient will give me partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z. How many minutes am I remaining with children?
5 minutes.
5 minutes. Okay. So now our job, our f is x squared plus y squared plus z squared. So our job is to find the first element. Okay. So what is the partial derivative of f with respect to x? So what does partial derivative mean? As the name implies, partially differentiating. So partial derivative, partial, you have a function. As you can see, this function has got three variables, x, y, and z. So normally, the total derivative, there's a concept of total derivative where normally, if you're derivating f prime, you are supposed to derivate with respect to each variable, right? All the three variables. But here, you're just differentiating with respect to x. Therefore, you're not completely differentiating. This is why you call it partial derivatives, okay? So the partial derivative of f with respect to x means that you only consider x as a variable and just for some unknown reason, just ignore the other variables. Ignore them, take them as constants. Assume that y squared is a constant. That is, for example, if I've got a function 2x plus 1. When I tell you to find f prime, for people who've forgotten how to differentiate, s'il vous plaît, you can check that up as well. That will be way, way beyond what I need to teach you. So I'm assuming we all know how to differentiate the power rule and things like that. So the derivative of this function is just 2. We ignore y. When we have a constant, we ignore it. When we find a derivative, then the derivative of 2x is just 2. So for now, just take it as a derivative of is just 2. And if you don't understand, you can also look at a video on partial derivative. It is going to help you. So the same way we ignored y, that's how we're going to ignore y squared and z squared. We're just going to take it as a constant. So what's a partial derivative of f with respect to x here? What's the derivative of x squared? We're applying the power rule. This is just going to give us 2x. Then this is a constant, so you take it as a constant. So the partial derivative of constancy, the derivative of constancy is 0. So in the same way, we're going to carry out the second component, which is the partial derivative of f with respect to y, which is going to give us c. So here you're going to ignore this and this. You only take y. Okay, so the derivative of y squared is 2y. Okay, then last but not the least, you're going to find the partial derivative of f with respect to z, which is going to give us what is z squared? So 2z as well. So therefore, very simple. Therefore, your gradient of f given this function, your gradient of f given our f is equal to the first component gave us 2x, the second component gave us 2y, the other component gave us 2z. Okay, if I want, I can just do everything, then I can say x, y, and z. Okay, if you leave your answer like this, I'll mark you because I know this is a vector. But it's much advisable because since you're working with vectors, so gradient Remember, f was just some scalar. It's now feeling confident because it has direction. You've given direction to this scalar, which had no direction, only magnitude. So it's now feeling confident. The gradient of f is equal to 2x in the direction of e, okay, or ex plus 2y in the direction of g, then plus 2z in the direction of k. You can, if you leave it like this, I'll give you extra points, okay, because you're getting familiar. So we had f, which was a scalar. Now gradient of f is now a vector. Why? Because it has got both magnitude and direction, magnitude and direction. So that is an example on how we
One
find
more minute left.
1 minute. 1 minute left, or your call ends in 1 minute.
Yes,
Okay.
one minute. 1 minute.
Okay, because the people don't have electricity and things like that. Let us join next time. I don't know what time it will be, but with physics, civil play, I would urge every engineer to join. Also advise your engineers to join my lessons next time. We're going to end it from there. Don't forget my homework. I'm also going to send the other works. Make sure you check on partial derivatives, how to do partial derivatives, and things like that. Then I'm going to give you a homework. Oh, wait.